Hi class, we are looking at figure 14-4 in your Ruddiman textbook, and what this shows is the oxygen isotope ratio incorporated into forams or plankton shells. So if you recall, a couple weeks ago we were learning about different types of isotope ratios, and these are stable isotope ratios, so they do not decay over geologic time. And oxygen 18 is a heavier stable isotope of our more common oxygen 16. And remember, elements are always defined by the number of protons they have. So 16 is the most abundant. Oxygen 18 is an isotope of oxygen. Now, these del 18O is the oxygen isotope ratio, so that's looking at the ratio of oxygen 18 to oxygen 16, and it's looking at that compared to a standard ratio of oxygen 18 to oxygen 16, and that standard is VSMO, the Vienna Standard Mean Ocean Water Standard, and that's set at 0 per mil. So remember that this little symbol right here is per mil, right? So if we took away one of those little O's at the end there, that would be a percent, which is per 100. A mil is per 1,000. So we're looking at this in terms of thousandths. So these are much smaller ratios than, these are an order of magnitude smaller than a percent. Okay, so when an isotope ratio is more negative, that means there's less of the heavy isotope present than that of the standard. So now looking at this, the standard for ocean water is around 0 per mil. And so now thinking about glaciers. So when water freezes, when ocean water freezes well, let's see. So water evaporates from the surface of the ocean, right? And what evaporates is the lighter oxygen, O16, and that goes up into the atmosphere. So the atmosphere is depleted in O18 compared to ocean water, right? And then that gets incorporated into clouds, which condense and precipitate down to the surface again, and the accumulation of snow over time forms a glacier. And so lighter oxygen isotopes get incorporated into glacial ice. And so we have more negative del 18O values, so these oxygen isotope ratios in ice, usually about -35 to -30 per mil. And so looking back at the deglaciation, when these glaciers are melting, we have this meltwater dumping into, for example, the Mississippi River. And so we have these lighter isotopes of oxygen getting dumped into the Mississippi. And I'm just trying to locate my pen. Here it is, my pointer. And the Mississippi empties into the Gulf of Mexico. So all of a sudden, there are these pulses of these lighter isotopes of oxygen. And organisms get really excited when there are lighter oxygen isotopes available for them to use, because it takes less energy for them to incorporate it into their shells. And so the little forams living in the ocean are incorporating this into their shell material, and when they die and they deposit themselves onto the sea floor, these oxygen isotopes get preserved in the sediment record. And so what we're looking at here is this first graph right here is data from the Gulf of Mexico. And so on the top, we have present time is 0, and then down at the bottom of the y-axis is 20,000 years ago. And the x-axis, looking at the top here, shows negative oxygen, so lighter oxygen isotopes more to the right, so lighter fractionation, and heavier towards the standard to the left. And what we're seeing here is that we got these, the bulk of these meltwater pulses between like almost 18,000 and like say 13,000 years ago, right? So that's where you see this departure towards the right here. So these lighter oxygen isotopes were available. And we see a similar trend up in the Norwegian Sea here. So we see the same pulse. And so that shows a time of rapid melting and outwash of this glacial melt into the ocean, where plankton could incorporate it into their shells, and then then these isotope ratios were preserved in the geologic record.